Okay, thank you for staying with me and thank you for watching. Hello guys. Uh, I just solved this problem, shear moment diagram for this statically indeterminate beam, but I used, let me see if I have the papers. I'm always chasing my papers. Here, where you go. And I selected the reaction, the By, as redundant because this is statically indeterminate and has 1 degree of indeterminacy. So we selected this one as redundant, and that is in the previous video. Now, what if we select a different one? Let's say the moment at A. So if we select moment at A, I know that the deformation for this beam is gonna be something like this. No rotation, come here, deflect, and goes like that. Something like that. So if we select the moment as redundant, we have to make this happen. How do we do that? Then we're gonna have our primary structure is gonna be, if we take the moment out from this is basically a simple supported beam with that little cantilever over there. So basically it's gonna be this, like that. And this was a 0.5. 0.5 0.5 kip per foot. Yes, 0.5 kip per foot. So basically we have this, which is going to deflect something like that, and then we have to add our superimpose this with the other one. How do I get this with this rotation here into this? Then I have to apply to the same primary structure, which in this case is this. I have to apply a moment in this way, a rotation, a unit moment, and that unit moment is going to produce something like this, something like that. And when I add this plus that, then I'm going to get the original one that I needed to do with rotation 0 in this part. So let's try to do it in this way, and let's choose or select MA as redundant. First step. Okay, redundant. Now let's work with this one. If I select that as a redundant, what I'm going to have here is AY and BY, and I can do summation of moments at A equals 0, and if that is correct, then I'm gonna have this 0.5 times 0.5 times 0.5, 0.5 times 20 times 10. Remember, sometimes I do this and I know that you know it, but 0.5 times 20, that's gonna be that load there, times 10, that's gonna be the distance, negative, plus 15 by equals 0, so by is equal to 6.6 kip, and if we do summation of forces in y equals 0, this is 10, this is 6.6, so AY is going to be 3.3 kip. Repeat it. That. Now, if we study this one now, this rotation is going to be my flexibility, and this is going to be F, I'm going to call it FA, whatever you want to call it, FAA. FAA is the flexibility coefficient for a force at A applied at A. That's what it is. In this case, not the force and moment, but it's the same thing. And it's this rotation here. This is the rotation that is producing that. So if I use that moment over there, I can do the same thing. This is AY, this is BY, and I can do summation of moments summation of moments at A equals 0. And if you do that, you have this 1, positive 1, plus 15 by equals 0, meaning by is going to be negative 1 over 15. That means that dy is going to be acting in reality downward. And if I do summation of forces in x, now ay is going to be also 1 divided by 15 in this direction, 1 divided by 15 in this direction. So once we have that, we do the same thing. We do the deflection of the primary structure, the deflection of the secondary, of this structure here. In this case, it's not the deflection, it's the deformation. Remember, this is what we are doing, deformation of the structure. So let's do that. For this one, we're gonna, last time we used section 1 and section 2. Section 1 and section 2. So let's try section 1 and section 2. 1, 1, 2, 2. And if I do that for the primary structure, primary deflection of primary, which is that one, primary structure. So then remember, in this case what we are basically calculating is the rotation, and 1 times the rotation is going to be equal to the summation of all the m divided by ei dx. Now let's start with the section 1, section 2. I mean, I don't know if it's worth it or it doesn't worth it, reality. Let me think. Should I do this or should I not do that? I think so. I think I should do that, because if I start thinking of this structure here, you know, this part, when I study this part, it's gonna be 0, the same thing that happened before. So I might use only the section 1 in this case. Now let me change something so you can practice also. In the previous case, in the former case, I did my section from here to here. Now I'm gonna do my section from here to here. No, not any, and this is the primary structure, not any particular reason. So I'm sorry, I made the sections there, but it's supposed to be here. Okay, not any particular reason, it's just for you to get used to doing it either from left or from right. So if I use that from this end, I'm going to have basically that. This is going to be my reaction, ay 3.3, like that. And this is going to be my section, so 1, 1. And this is going to be my m, big M. This is going to be x, and this is going to be v. And remember, that value is 0.5, and this is going to produce a force 0.5x at 0.5x divided by 2. Summation of moments right there equals 0. And then you're going to have negative 3.3 times x plus 0.5x times x divided by 2, because remember this distance here is x divided by 2. So it's going to be plus 0.5x squared divided by 2 plus m equals 0. M equals negative 0.25 x squared plus 3.3x. There you go. We have m. And remember, this thing that we are doing is section 1, section 1, section 1, x is measured in this direction from 0 to 15 in the primary structure. Now the section 2, this section 2, for the section 2, I'm going to do the same thing, but I'm gonna take it from this part just for practicing, so you lose the fear of doing it from any direction that you want to. So if you do that, this is gonna be x. This is gonna be my section 2 in the primary, and the primary is gonna be from 0 to 5, 0 to 5, that's what it is. People keep texting me now. 0.5, and then I'm going to have this M and this B because I'm using the other side. Remember, I'm going from left to right. Yeah, keep going. Keep going. I'm gonna mute everything when I'm recording a video, and I always forget. Summation of moments here. Here. So this is gonna be what? 0.5x times x divided by 2. M, so negative m minus 0.5 x squared divided by 2 equals 0. So m is going to be equal to negative 0.25 x squared. And that's the primary structure, section 2.2. Now when we go to the virtual part, this one, let's do the same thing. Let's section 1.1 and section 2.2 in the same way that we did it before. So section 1.1. Let me put here the virtual structure. The virtual structure is going to be this one. Section 1.1 is going to be here, and section 2.2 is going to be here. Section 1.1. What do? We make the code over there, and we use the same. Remember, here we use from here to here. Here we're going to use from here to here also. So what do we get there? We get this. We get a moment of 1, but the moment of 1 is in this direction. This is the moment that we have over there, and we have a reaction. This is the moment of 1. This reaction is 1 over 15. And this is the distance x, and we have our small m and our small shear. And this is going to be my section 1.1 for virtual from 0 to 15. So what is this? This is going to be summation of moments right there equals 0 in this direction. So we're going to have m minus 115x plus 1, m minus 115x plus 1 equals 0. So m is going to be equal to negative 1 plus 1 over 15x. And for the section 2.2, which is 0 to 5, with that section, basically, if you look at this, the section is here, right? What you have is this. Section 2.2 is here. This is x, and this will be m. So, but m is 0 because there's nothing. That's what I was hesitating to do this or not to do this. I'm just doing it for you to realize that if you look at this before, then you know that you don't have to calculate that. So once we have these two things together, the only thing that we have to do is just finish whatever we have. Now, deflection of the primary structure, the deflection of the real structure. Let's go. So 1 times my rotation is going to be equal to 1 divided by EI multiplied by the summation of all the integrals, but in this case it's only 1, and it's 0 to 15 because it's section 1.1, and then what you get here is negative 0.25 x squared plus 3.3, that one, multiplied by this one here, which is negative 1 plus 1 over 115 x dx. And once you solve this thing, it's gonna give you a rotation of negative 54.68 divided by EI. This is gonna be the rotation of the primary structure. Now, for the virtual structure, which is this one, we already have it because this one is the same as this one here. So the only thing that we have to do is apply it twice. And remember, that will be something like that. 1 times our flexibility coefficient has to be equal to the integral from 0 to 15 of m times m. So that means this square dx. And that means that our flexibility coefficient is going to be equal to 50 divided by 50. Is this 50? I don't know. No, I'm doubting. No, I'm doubting myself. It's 50. No, it's 5. I think. Yeah, it's 5, not 50. This is 5 divided by EI. That's what it is. You can solve it. I mean, and you're gonna get this value when you solve it. And then you go back and you apply your original, and you say this one has to be equal to this one plus this one. What is the rotation here? 0. So 0 has to be equal to the rotation that we calculated here, which is this one, negative 54.68 divided by EI, plus this one, 5 divided by EI, multiplied by the moment, because this was created by a moment of 1. Now we are multiplying this by the moment at A. And once we have that, we can say that our moment at A is 54.68 divided by 5, and our moment at A is going to be equal to 54.68 divided by 5. That's going to be equal to 10.93. Keep fit. Now, if you check what we did before, if I find it once again, where is it? What is it? Where are you? Here. Is this yours? Yes. So once we check what I did before here with the other problem, we calculated By when we selected By, and then with that By, we went and we calculated the rest of them, and look at the value of MA that we got. So what you have to do in this case is, now that you know the value for that, you go back to your original structure, which is this one. You put that value that you already know, and then this is AY, this is 15, this is 5, you have a distributed load here of 0.5 kip per foot, and the only thing that you have to do is finish this problem. Summation of moments at A equals 0, like that, and then you have 10.93, which is the moment that you already know, plus 15 By, minus 0.5 times 20 times 10 equals 0. 0.5 times 20 times 10, right there, equals 0. And then you can solve for By, and hopefully, please, it's going to be the same. So this is going to be what? 20, 200, 100, 100, 100.93 divided by 15. And the value is going to be, let me see, 15, 10.93, summation here, summation here, summation here, summation here. How much is the value that we should get? How much is the value that I should get? 5.94. Let me see if I get that value or I don't get that value. Summation of moments here, once again, 0.5 times 20 times 10, correct. And this is what? Positive, 10.9. And this is what? Yes. So 0.5 times 20 times 10. What? No. Minus 10.93 divided by 15. 5.938, 5.94 keep, which, if we do summation of forces in y equals 0, then AY has to be equal to 10 minus that, and it's 4.06. And those are the same results that we got before when we did the problem selecting the other one, selecting BY as a redundant. So you can select either, guys. It's up to you. It's whatever is easier for you. And that's about it. So keep watching. See you later. Stay safe.